any circuit can be analyzed by brute force application of KVL, KCL, and Ohm's law. This is called the exhaustive approach, and although it will always work, it's kind of labor intensive. In an attempt to save work, I introduced circuit reduction techniques. In circuit reduction, we combine circuit elements that are in certain configurations into fewer equivalent circuit elements, which reduce the number of unknowns we have. Unfortunately, though, not all circuits are reducible, which limits the applicability of circuit reduction techniques. In the next few videos, I'll talk about two very general approaches for reducing the number of unknowns in a circuit. These are called nodal analysis and mesh analysis. First, I'll quickly review the analysis approaches we've used so far. Our models for individual circuit elements are based on a relationship between voltage and current at the element's terminals. One example of this is Ohm's law. The interactions among circuit elements are governed by Kirchhoff's current law and Kirchhoff's voltage law. Using KVL, KCL, and the voltage-current relationships allows us to analyze any circuit containing only resistors and sources. In an attempt to reduce the effort required to analyze a circuit, I introduced circuit reduction techniques, including voltage and current dividers. In these techniques, we're still applying KVL, KCL, and Ohm's law. It's just that we're taking advantage of some shortcuts that certain configurations of elements make possible. However, the circuit has to contain these configurations of elements in order for this approach to work. This circuit, for example, is not reducible. None of the elements in this circuit are in either series or in parallel. No node interconnects only two elements, and no loop passes through only two elements. So, circuit reduction techniques won't help us analyze this circuit. With the tools we've got so far, we're stuck with the exhaustive approach. This approach requires that we define voltages and currents for every resistor. So, this would require 8 equations and 8 unknowns, which is pretty tedious for a circuit that's this simple. There are, however, other analysis approaches that do allow us to reduce the number of unknowns in this circuit. The two approaches I'll talk about first are nodal analysis and mesh analysis. I'll provide details about how to apply these techniques in later videos, but for now I just want to give an overview of what's involved. Although either technique can be used to analyze any circuit, it's important to be able to use both, since, depending on the circuit, one or the other technique may result in fewer unknowns. Both of these approaches provide a rigorous approach towards defining a reduced set of unknowns and writing equations from which you can solve for these unknowns. And both methods allow you to determine anything else you want to find out about the circuit from the identified unknowns. Since we want the fewest number of unknowns and equations, I'll spend time in this video talking about determining the number of unknowns in each approach. In later videos, we'll talk about the details of each analysis. In nodal analysis, our first step is to identify the independent nodes in the circuit. Our unknowns are the voltages at these independent nodes, which are called the node voltages. Then apply KCL at each of the independent nodes and use Ohm's law to write KCL in terms of the node voltages. This will give the same number of equations as unknowns, so you can solve these equations to determine the node voltages. Once you have the node voltages, you can find out anything else about the circuit that you want to determine. Identifying the number of independent nodes is important, since that'll tell you how many equations you need to write and solve. Next, I'll give you a few guidelines about how to determine the number of equations you'll need if you use nodal analysis. Independent nodes are separated by circuit elements other than voltage sources. The nodes at the terminals of a voltage source are not independent. In this example, there's a 10-volt difference between this node and this node. The voltage difference between these two nodes is known. I don't need to create two unknowns there. I can eliminate the voltage source. Now, this becomes one independent node. This is another independent node, and that's my third independent node. So I have 3 independent nodes. If I have n independent nodes, I'll end up with n-1 unknowns and n-1 equations. So for this example, I'll have 2 equations and 2 unknowns. This isn't entirely true, but it's a good guideline. I'll provide more details later when I talk specifically about nodal analysis. The first step in mesh analysis is to identify the mesh loops in the current. The unknowns are the mesh currents, which run around the perimeters of the mesh loops. Once you've identified mesh currents, apply KVL around each mesh loop and use Ohm's law to write Kirchhoff's voltage law in terms of the mesh currents. This gives the same number of equations as unknowns, so you can solve these equations to determine the mesh currents. Once you have the mesh currents, you can find out anything else about the circuit that you want to determine. Identifying mesh currents is important, since that'll tell you how many equations you need to write and solve. Here are a few guidelines about how to determine the number of equations you'll need if you use mesh analysis. Mesh currents go around the perimeter of enclosed non-overlapping areas after you've removed current sources. If you define them efficiently, no mesh currents will go through current sources. This circuit, for example, will have two mesh currents. I know the current through the current source. That is not unknown, so I can remove the current sources. That leaves me with two enclosed non-overlapping areas. My mesh currents will go around the perimeters of those areas, so I'll have 1, 2 mesh currents. As with most rules, there are exceptions to this. I'll provide more details about how we can account for the current sources later when I provide more details about mesh analysis. Those are the basic ideas behind nodal and mesh analysis. Keep in mind when watching later videos that the first step is always to choose which analysis approach you want to use. If you're going to choose nodal or mesh analysis, make sure you check to see which approach gives you the fewest number of unknowns. Generally, more errors occur when solving the equations than when writing them. So, the approach with the fewest number of equations will tend to result in fewer errors. This means that a little extra time spent up front deciding what approach to use will pay off in the long run. The next few videos will cover the details of nodal and mesh analysis.